Stanford University.
So we have an exciting talk, the third talk of the session of the day. This is Matthias Fuchs. He got his PhD from the Max Planck Institute for Quantum Optics in Munich in 2011? 10. Oh. And then after that, he joined SLAC in our group, actually, where he was a postdoc for, well, not even 2 to 3 years.
2 to 3 years, yes.
And after that, he got an appointment as an assistant professor at the University of Nebraska in Lincoln. So, so we miss Matthias a lot. And he's going to tell us about these very exciting new developments in nonlinear X-ray optics. Thanks, Matthias.
Live? Yes, okay. Thank you, Mariano. Thank you for inviting me. Thank you for having me here in this exciting summer school. I will be talking about, as Mariano said, nonlinear X-ray optics. A brief outline of the lecture. So when I put together the lecture, I was putting in some thoughts, and I decided that I want to have rather not showcase a whole bunch of experiments and different concepts, but focus on a few and go into a little more details on the few. So we can go a little bit more into the physics behind it, but the other reason being that there also is not that many more experiments yet, because it's a fairly new and young field. So I will start out with talking about some theory. I will be mainly talking about scattering, parametric scattering processes. I'll start out with talking about nonlinear optics and introduce you to nonlinear optics at visible wavelength first. Talk about the anharmonicity of the atomic potential, the free electron gas nonlinearity, and then nonlinearities at X-ray wavelength. And then I will, with all that we have learned in that part, then I will talk about experiments, nonlinear X-ray optics experiments, specifically about parametric down conversion, X-ray optical sum frequency generation, X-ray second harmonic generation, and close with nonlinear X-ray Compton scattering. This has been introduced and used this morning before. As you can see, we spared no cost for you here at the summer school. We provided you with an audience response system. I will show you in a bit how we're going to use it. I know half of you guys are jet-lagged, the other half just had a big lunch and/or just came out from the California sun in a dark room. So I will keep that lecture a little bit interactive, ask you some questions here and there so you can respond. There will be a little indication at the top right corner of the slide. I will also tell you when you're supposed to give an answer. The answers can have one or multiple answers to the question. It can have answers. I said we didn't spare any costs. There's even 2 response systems. The other one is this. It looks like that. Most of you have it. It can be applied by either the raising or the lowering operator. This can also be used at any time during the lecture, and it's also encouraged. Okay, let's start with the color sheet. First question for you guys. How confident with the audience response system are you? Yellow, I have a color sheet, I'm not afraid to use it. I already have a paper cut. I'm folding challenged. Some folding challenged, some yellow, red. Yes. It's good that there's no plain green or plain blue because there wasn't an option. But okay, so you figure that out. Okay, let me introduce you to nonlinear optics. There's actually great quote from Yen Shen's in his book, Principles of Nonlinear Optics. Physics would be dull and life most unfilling if all physical phenomena around us were linear. Fortunately, we are living in a nonlinear world. While linearization beautifies physics, nonlinearity provides excitement in physics. Okay, so this is a really brief introduction. The next question for you guys, now more serious. How much experience with nonlinear optics do you have? Yellow, I live in a linear world. Red, in general, I know about nonlinear optics, but a refresher would be good. I use it daily, at least once every morning and once before I go to bed. Or nonlinear is my second order name. Okay, I see some green, some it's okay. I think it's a broad bandwidth. I would say. So most of you guys are probably somewhere here in between. So I hope that I can address all of you. I hope I won't bore all of these guys, Mr. Nonlinears, and I hope I won't be too fast for all the linear people. So I will go into some detail into the background and then into the physics, and then hopefully everybody is turning green after is green after the talk. Okay, some nonlinear optical behavior. What is different between linear and nonlinear optics? Well, in nonlinear optics, the principle of superposition is violated, which is often used in linear optics. Also, partially as a result, you can have, if you have a strong beam, the frequency of the strong beam can be changed while it propagates through a nonlinear medium, as you can see here. The generation of two red beams come in, second harmonic generation, and you see a blue light come out. And unlike in linear optics, in nonlinear optics, photons can actually interact with each other through the nonlinear medium. What you see here is a Feynman graph of light by light scattering. There will be scattering in vacuum. For that, you use vacuum nonlinearities. For that, you need extremely high fields. We focus more on interactions in a medium, where you can also have light by light scattering. And as you all know, as you probably now have figured out, if you talk about light by light scattering and applications of light by light scattering, the most obvious application, of course, is lightsaber fights. So nonlinearities is basically the only way in the physics behind lightsaber fights. Okay, so if I haven't scared any of you out and you all are excited about that, then I can actually go into more physics. Let me start first with the first nonlinear optics experiment done by Franken, 1961, just briefly after the laser was invented. The experiment was, he used a ruby laser, focused the beam onto a crystal, where he generated second harmonic radiation, and then spectrally dispersed the beam into the fundamental, and it generated second harmonic. It was a very weak beam because it was not phase matched. What that means, I'll go into more detail later. And if you look at the paper, what was actually published, so here's the spectrum, this is the fundamental beam, and here is supposed to be the little dot, in case you don't know that, but here's what the dot is supposed to be. But some very eager person at PRL edited out because he thought it would be as much. So there's actually the real data is gone from the publication. Okay, just as a warning, as I said before, I will mainly talk about parametric scattering processes and one non-parametric scattering process. But I will not talk too much about nonlinear absorption experiments. There have been a lot of beautiful experiments done, but I focus more on the scattering process. And as a second warning, I will be switching between SI and CGI units at times. So it will be factors of C, epsilon naught, pi's, forget about it. Okay, if we talk about light-matter interactions, I will be very basic about that, and we keep it very simple. So we keep a very, just a classical model where we have a nucleus, an electronic charge cloud around it. This is our atom. And now if we apply an electric field, of course the electric field or electromagnetic wave, there will be a Lorentz force onto the charge distribution. And the Lorentz force given by this equation right here. And the charge distribution, the center of mass, will be moved, will be displaced by a displacement delta x. And all of this process then induces a dipole, which is just given by the charge times delta x. Okay? Now this is for a single atom. If you talk about a material, now you come in with your electric field. You have a material with lots of dipoles, say identical dipoles in this case. They all, the electric field induces dipoles in the material, all of them. You average over it. And what you get out is the macroscopic induced polarization. So this is a macroscopic quantity, and it is given by this equation right here. So the polarization n is number of dipoles. This is our induced dipole, and that is equal to chi, which is the susceptibility, times E, the electric field. And we will be talking about the susceptibility quite a bit in the next few slides, so it's just to get you started. And also for as a primer, this induced polarization will act as a source term in the wave equation, and that is actually the fact why you have or why you can get to nonlinear optics and the generation of different frequencies than what you send into your nonlinear crystal. Okay, so one quick word about the susceptibility. It's a constant, it's material and frequency dependent. It basically tells you, or is a quantity about the strength of the atomic response to an applied electric field. And it is related to the index of refraction, where index of refraction squared is just 1 plus the susceptibility. And as we said before, the atomic polarization that is induced by the applied electric field is given by this equation right here. It's linear, as you see, so if you have the electric field, positive, negative, you induce a polarization that is right there. All right, so this is the polarization. You see up to about 10 to the 9 volts per meter. But how about we want to live in a more exciting world? We want to get it a little bit more nonlinear. So how about we just tune it up to, say, 1 trillion volt per meter? Okay, 1 trillion volt per meter. You plot it, and you see that the polarization now starts to deviate from the linear induced polarization. And here is where we have first nonlinear terms. And as this is not linear anymore, what we need to do is the polarization, where we just use the first term right here. We actually see that there's multiple higher order terms, chi2, chi3, that depend on the electric field squared and to the third power and so on and so forth. And when we talk about nonlinear optics, these are the terms that we are most interested. Okay, so this is again the polarization, and just to give you a feel for a few numbers, the typical field strength that you require to see this nonlinear behavior, at least at optical wavelengths that is on the order, when you have electric fields that are on the order of the atomic field of the atom, which is about 10 to the 11 volt per meter. Or if we calculate it in intensities, it's about 10 to the 16 watt per square centimeters. So this is at optical wavelengths. You guys are all here because you're interested in X-rays. So you know that LCLS is just around the corner here. Turns out that if you focus the LCLS beam to a small spot size, you can actually get fields that are about 2 orders higher than the atomic field. So now you would say, well, here we get nonlinear effects. Now we should with LCLS, we should just have plenty nonlinear effects, just be buried pretty much in nonlinear effects. But I'll show you in the next few minutes why this is not the case and why it is still a very young field. Okay, another question for you guys. So what do you think, what type of an X-ray source do you minimally require to observe nonlinear X-ray effects? X-ray tube, a synchrotron, XFEL, or not yet invented? Okay, I see blue, I see some green. People who hold up green probably want to get out into the sun. They don't want to see the experimental part. Some red. Okay, I see 1, 2 yellow, very, very bold yellows. Okay, X-ray tube. As it turns out, it is actually yellow is the correct answer, X-ray tube, surprisingly. There has been an experiment in 1971 demonstrating the X-ray parametric conversion. They used an X-ray tube, and we'll go into this experiment a little later. We'll show you what the experiment is, why they can get away with just using an X-ray tube. They took about 400 hours of data, a maximum event rate of about 1 event per hour. And just if you compare that, you guys, if you have been at LCLS, so 400 hours is about 33 LCLS shifts, 12 hours each. That is probably a scientist's lifetime these days of LCLS shifts that we will ever get, if you get lucky. Okay, let me get back to the physics of nonlinearities. So when we talk about nonlinearities, basically the reason why we get this nonlinear susceptibilities is because we drive the electron beyond the linear or the quadratic potential, linear restoring forces, where the media displays some nonlinearities. There's 2 types: non-centro symmetric medium, which shows the lowest order, a chi2, so our chi2 polarization. Chi2 is the reason why we see, for example, second harmonic generation or some indifference frequency generation. There's also centrosymmetric media, where the chi2 is equal to 0, which means the lowest order is a chi3 process. And here you have third harmonic generation, 4-wave mixing, self-focusing, self-phase modulation, and so on and so forth. Okay. Question for you guys. So I have a dry field. It looks like this. My linear induced polarization just follows the dry field, as we said, since it's linear. Now, if I have a polarization that looks like this or like this, the question for you guys is, what are the corresponding crystal potentials? Is this here a centrosymmetric and this is non-centrosymmetric? Or this guy is non-centrosymmetric and this guy is centrosymmetric? Okay, I see mostly yellow, 1 blue. Okay, mostly yellow. That, of course, is correct. It helps. So now if you plot so this is our nonlinear polarization. If I just plot the linear polarization, and then if I plot whatever frequencies I need to add in order to get to my nonlinear polarization, you can see here it's basically a combination of the linear of omega, the linear polarization, and the 3 omega, third harmonic, and I get to this centrosymmetric medium or polarization. And here it's a combination of omega and 2 omega and a constant offset, and I get to my nonlinear polarization of a non-centrosymmetric medium. Okay, so back to our model. So we said we have Enharmonic potential. The way we do this here, again, is a classical model. The classical model is good to understand the physics behind it. You can do a quantum mechanical model, but it's more calculation intensive, and it's not quite as obvious what the physics is behind it. The classical model fits surprisingly well, except if you have multiple resonances in an atom, but for a single resonance, it actually fits quite well. So what we do here, as an example, we use a non-centro symmetric media, shown here. And now we just include the enharmonicity as a quadratic restoring force of strength A. So here's your equation of motion of the enharmonic oscillator. We just add this ax squared term here. It's a driven oscillator. The field that drives it is the sum of omega 1 and omega 2, so we have two frequencies go in, two components. And now since this is this differential equation with this input does not have an analytical solution, so what you need to do is we use perturbation theory to solve this equation. And the way we do that is that we take our electric field, replace it with lambda times the electric field, where lambda is an expansion parameter that we set equal to 1 at the end of the day. And then that will allow us to expand the displacement that we're calculating of the electron moving in the potential by, we say, so this is our x, so we have a lambda first order plus lambda square second order and lambda to the third order, and so on and so forth. What we then do is we sort this equation by powers of lambda and just solve it iteratively. So first lambda equals 1. So first order equation of motion, and given here, you all have calculated a million times. It's just a driven harmonic oscillator. This is the solution to it. So we have amplitude and the field, or the motion of the electron just follows the oscillation frequency of omega 1 and omega 2. The oscillation is at the frequencies, again, of the drying fields, and the amplitude is just given by E over m, electric field, divided by d, where d is given by this expression right here. Our omega naught is the resonance frequency. Our omega j's is the frequencies of the field. And then we have a damping part, and this is basically your Lorentzian line shape. Okay, that was the first order. Now we use our result for the first order and put that into our lambda square, our second order equation that you can see here. So this is the first part of the equation. Here you can see that we plug in our first order, our result from the first order displacement. I don't want to go through the math. You can do that all yourself, but some math later. We will get a second order solution again, give as a function of time. So we again have an amplitude, but now you can see that the oscillating the second order term now starts oscillating at twice the input frequency, and now we all of a sudden have generated light at a different frequency, or at least we oscillate at a different frequency, which we can then generate light at a different frequency or different from the input field. The amplitude is given now by our A was the enharmonicity parameter of the potential or the force. The field squared, and then we have a d and a d squared term. Again, the d's is just replace your frequency in that. And as you see, your squared term of your first order displacement also has solution at 2 omega 2, the sum, the difference, and omega equals 0. Okay, now we know what the displacement is. And now we want to get back to the susceptibility. Remember what the susceptibility is. So what we do is basically we compare the higher order terms of the susceptibility and the different polarization, two expressions of the polarization. Remember, the polarization is given by the second order. The second order polarization is given by the second order susceptibility times the field squared. Our second order polarization is also given by the displacement, second order displacement times the charge pretty much. Compare the two, remember that x is given by this, the amplitude is given by this guy. And then from that you can get the second order susceptibility given by this equation right here. So again, here's our A and our D and D square, right? Okay, a quick discussion for that, so you get a feel again for the numbers. So we have, we want to get a number for our chi2. What we need to do, we have to find out what this A is, this anharmonic coefficient, and we can estimate what that approximately is by saying, well, if we will have a nonlinear effect, if the linear and the nonlinear restoring force, they become comparable. Basically, when the electron displacement is approximately at the lattice constant of our crystal, lattice constant d. So you say this is the linear force, this is the quadratic force, omega naught d, ma d square. From that we can calculate A is omega naught squared divided by d. So again, omega naught is just the resonance of our atom, d the lattice spacing. And we can say for non-resonant radiation with frequency much lower than omega naught, and if we assume that n is roughly equal to 1 over d to the third, that's the density of the electrons, you can basically calculate chi2, and now it's just pretty much given by these constants, divided by omega naught to the fourth, d to the fourth. And as it turns out, for most solids, actually d and omega naught are pretty much the same within an order of magnitude. And from that, you can roughly estimate that your chi2 is about 10 to the minus 12 meters per volt. So it's a fairly small quantity. But again, we want to apply big fields. And if you calculate what kind of field you need in order for that first order polarization term to be equal or roughly equal to the second order. So remember, the first order is about 1. It's proportional to your index of refraction, and typically you have an index of refraction of a few. So this is on the order of 1. If you do that, if you calculate what fields you need to become, for these two terms to become comparable, here again roughly at your atomic field strength, or so 10 to the 11 volt per meter, or about 10 to the 16 watt per square centimeter. So that turns out all right. Okay, another question for you guys. Now, how does the second order susceptibility due to the enharmonicity of the atomic potential scale with frequencies? Now, not in case of a very small frequency, but very high frequency. So basically, if our incoming frequency is much higher than our resonance. So again, here's our chi2, here's d. What is the scaling? Less responses than for the first question. I can see some red, some red, some green, some blue. I think if I would put a number, it's a fairly broad spread, but it's probably mostly green, which is actually the correct answer. Okay, so basically you just forget about your omega naught because omega j is so much bigger than omega naught. You have here a d square, which each d gives you 2 orders of magnitude in omega, which means you overall get a scaling as omega to the minus 6. So green, correct answer. Yes? With the exception of A, but this only has omega naught and no. This is static and does not have a frequency of the incoming field. Okay. Now the susceptibility scales as omega to the 6, or 1 over omega to the 6. which means that now we want to go from optical radiation to X-ray radiation. If our susceptibility scales to the omega to the -6, what do you guys think, what fields do we actually need to see second-order effects due to the anharmonicity of the atomic potential? When do they become important? Say for X-ray radiation, 10 keV photon energy, assume an atomic resonance of about 1 eV, and remember that for linear optics, I should say for visible optics, the second term became important at about 10 to the 11 volts per meter. The back of your color sheet has white space. You can put a few numbers if you need to. It's multi-purpose, so you can use it the way you want it. I see some answers filing in. Some green, few blue. Okay. So it looks like either it's going to be green or it's going to be blue. Okay, so we said it scales as omega to the 6th power. Now, the correct answer actually is blue, 10 to the 19 volts per meter. How do I get to that? Again, we said that we want to have the second and the first and the second order term be roughly equal, which means this is first order, second order times the electric field. Electric field is just chi1 divided by chi2. What some of you saw and others did not see is that chi1 also scales as 1 over omega squared. There's a little sneaky right here. Chi2 scales as 1 over omega to the 6th, so we all have about a scaling of omega to the 4th. We said the atomic field is about 10 to the 11 volt per meter, 10 keV photon to the 4th, so this gets you 8 orders of magnitude, so you talk about 10 to the 19 volts per meter. Now, I remember when I talked about light-by-light scattering, the quantum electrical critical field is about 10 to the 18 volts per meter, and that's when your vacuum starts bubbling. You see nonlinearities in the vacuum and all sorts of stuff. So clearly, these fields are far out of reach at this stage right now. If we ever reach these fields, then you will actually see real light-by-light scattering in vacuum. So we need a much higher fields for the nonlinearity, which means that we actually will have to look for a different nonlinearity. Before I do that, I'll just continue here for a few minutes to talk about one more very important property, which is the phase matching. So basically, what we talked about now, we have the susceptibility. Then we calculated the current that is oscillating in our material, and now from this current, we want to, or the induced polarization. And from that, we want to now calculate what is the field that is generated. The way to do that is that we use the inhomogeneous wave equation right here. We use the polarization, nonlinear polarization, as a source. And in case of second harmonic generation, where our omega 1 equals omega 2 equals 2 omega, and if we assume no pump depletion, which means our electric field 1 is constant, and the E2 is the generated second harmonic field, where the field is given by this. So we have e to the I k1 z omega t. Here we have k2 minus 2 omega, so this is our second harmonic field. K is just the wave vector, or wave number in this case, so it's n1 omega over c, and 2 omega over c. Now if we use all of that, use what is called a slowly varying amplitude approximation, so we can have the second order gradient of E2 approximated by this equation right here. Plug in the second time derivative of the electric field. We know that the polarization, second order polarization, is just the chi2 times the electric field squared. Okay, you pack all of this into this equation. Out comes this equation down here. which tells you about the evolution of the nonlinear field throughout your crystal. So basically this is your dE2 dz, the change of E2 with length propagation distance z is proportional to chi2, the electric field 1 square, and then we have this phase term right here, which turns out to be very important. Typically, or often, if you talk about intensities, you just get rid of the phase. Here, the phase is very important. And this delta k is actually called the phase mismatch, which is given by 2k1 minus k2, which again is the other wave numbers. Okay, why is this important? Again, k1 and k2 given here. Well, this basically tells you if the fundamental and your second harmonic have a different phase velocity, they will get out of phase. Energy then will first be transferred into the second harmonic. If you get out of phase into the wrong phase, energy will be transferred back into your fundamental. And you can see here from this equation already, if k is not equal to 0, you will have a sinusoidal oscillation. Right here you have an oscillating term of the second harmonic intensity along your crystal, and this is what is shown here. If you have a large phase mismatch, you can see that the intensity increases, decreases, increases, decreases, and so on and so forth, with a higher frequency. As in, if you have a small delta k, you can actually see that that the frequency then decreases of your phase mismatch. Another way to look at this is, of course, if we say we have second harmonic generation, which means what we do is we come in with omega photon, omega 1, omega 2, and we get out a photon of omega 3. They're equal to each other, which is the energy conservation. And the phase mismatch is basically the momentum conservation in this equation or in this process, that you have to have that K3 has to be equal to K1 plus K2. Okay, now if you calculate the intensity of the second harmonic, say you have a crystal of length L, calculate the intensity at length L. What you see here is this, you get to this equation right here. What you see, what I want to point out here is that we have a quadratic dependence on the incoming intensity of your fundamental. It's a second order process, so this is what you would expect. A quadratic dependence on L on the length of your crystal. It's basically a coherent amplification. And then you have this sink term right here, where you can see if your delta k equals 0, your sink is pretty much 1 and then drops off as you have a phase mismatch, drops off quite rapidly. So you want to pay attention to your phase mismatch and want to keep that as small as possible. In the optical, what we do, so for phase matching, again, this is our phase matching, K1, K2. In the optical, as you know, we have normal dispersion. This is your refractive index as a function of frequency, which means what we want to do, we get delta K0 if the index of refraction of 2 omega equals the index of refraction of omega. Not possible with normal dispersion, but what you can do is you use birefringence. You use an extraordinary and ordinary beam. They have different indices of refraction. Use the extraordinary beam as a pump. The ordinary beam will be your second harmonic. You can see that you can have the same index of refraction for both frequencies. You're phase matched, which means you're very efficient and you can convert energy quite efficiently. Okay, so much for the first part, the enharmonicity of the atomic potential. I basically walked you through how in optical radiation or optical wavelength, how we look about nonlinear processes. Then showed you that it's not possible for X-rays, so we're back to the start. So we have to find a different nonlinearity, which I will now talk about the free electron gas nonlinearity. But we did all of this. There was a reason behind it. So now you know all about phase matching. You know about nonlinearities. Now we just take this to a different step where probably not so many people usually use this free electron nonlinearity. Okay, what is the free electron or quasi-free electron nonlinearity? Basically, for X-ray photons, if you talk about X-rays, their photon energy is usually well above the binding energies of, say, at least most low-C material. The frequency is well above any critical plasma density for solids, which means that the electrons in your solids can just be approximated as quasi-free, which is also called the impulse approximation. And that we consider our solid basically just as a collisionless plasma with frozen ions, similar to here, but now just quasi-free electrons. We don't care much about the ion potential too much. And now again, if we send our electromagnetic pulse in, you will have the Lorentz force again. Previously, we didn't care about the magnetic field, but now we actually use the magnetic field as the source of our nonlinearity. We do that similar as we did it before. So this is our equation of motion right here. We say our V cross B term, the magnetic field term, is small, so we just treat it as a perturbation. So again, we have a lambda here. We can have the displacement. We can Taylor expand the displacement like this. Okay, I'm missing a lambda square here. Sorry about that. Now again, if we use an input field with two frequencies, like this, we can calculate it, plug it all in, and we have a first order result displacement, which is again basically just your field without the magnetic field. And you can see this is just the amplitude, the oscillation at omega 1, and the electron basically just follows the electric field in its oscillation. In a second step, we can use this, plug it into our second order equation, and then we get a beast that looks a little more challenging and more interesting down here. And what you can see, what I want to point out here is that you can see here again that it starts, that this oscillates at a frequency of omega 1 plus omega t. So here's basically again the source for your nonlinearity. So question for you guys. Assume that we have omega 1 equals omega 2 equals omega, so omega 1 and 2 is the same. Now what kind of motion does the electron perform? So remember you have R1 oscillates at omega, R2 is the second order, oscillates at 2 omega, you have these terms right here, and your R is given, your displacement is given by that. Now the answers are yellow, sinusoidal, red, figure 8, figure 16, or elliptical. I see lots of left-hand rule being applied and right-hand rule and vector products, and be careful not to break your second audience response system there, that your broken fingers, SLAC will not reimburse for broken fingers in this experiment. Okay, so I see mostly there's some red, some green. The answer actually, in fact, is figure 8 motion. If you go through it, it actually looks like this. So the electron trajectory for an electron in a large magnetic field, polarization like this will look like a figure 8 motion, where you have a oscillation. You can decompose this into two parts, or two oscillations pretty much. One oscillation that follows the polarization at omega. The second that is longitudinal, that's this guy right here, which points into the direction of the wave propagation, that oscillates at 2 omega, and then overall you get a figure 8 motion. Okay, now since this was already so much fun, we take this a little further because we need to use a little more rigorous treatment. we need to also take into account the spatial variation of the electron density rho and the velocity of the electron. So we need to use some modified equation of motion where we assume a plasma with no pressure gradient. But instead of just the Lorentz force equation, we also get a gradient of the velocity in here. We also use the continuity equation given right here, where we have the gradient of the density. And now we have lots of parameters to expand. We have the density, where we have the initial density and perturbations to the density. We have velocities, first, second order, and we have a current density, first and second order. And the current density, the first order current density, is actually given by the 0th order density times the first order velocity. The second order, you have two terms, a 0th order density, second order velocity, first order density, first order velocity. Okay? Now if you, again, use our driving field as we had before, this is our current density, our second order current density. You use Maxwell's equations. Some math later, you get to a second order current density here that oscillates at the frequency omega p, which is omega 1 plus omega 2. And it looks initially a little bit nasty, but I will just talk you through that a little bit, show you what it all means, and then it will become a little bit more obvious. First, so these first two terms come from this guy. The third term comes from this guy. Okay, so we have three terms. And what is the physical picture? Where does it come from? So we went through the math, but what is the physics behind it? Well, basically what you have, the electron is driven by our electric field 1. It acquires a velocity v1 and a displacement x1, which then leads to a second order velocity with a frequency component, which is the sum of omega 1 plus omega 2. And due to now, the first term is the Lorentz force term, the v cross b term, v1 crossed into b2. So this is just your magnetic field here, basically. 2 is the displacement. The displaced electron samples a different portion of the electric field 2. So you have your gradient of the electric field here, 2. And the third one is the Doppler shifted reflection of the electric field 2 from an electron moving with velocity 1. Okay, so that's the physics or the processes behind it. And now let's go and see what that all means. First, now, before I showed you or I talked to you a lot about anharmonic nonlinearities due to anharmonic potentials, we went through all of that, figured out that's not possible. To not make you go through this exercise again, we first figure out what is actually the strength of this nonlinearity before we continue, so we don't waste even more time. So for that, let me just take a look at this first term right here. They're all approximately equal in magnitude, but let's just take a look at this first term. Remember that the current is just rho times v, the second order velocity. If we have the same omega 1 equals omega 2 and the electric field equal to, we could just rewrite this guy as the k divided by omega 3 times the 2 electric field divided by omega to the third. So this is the second order velocity of this Lorentz term, of this free electron gas term. Remember the anharmonic potential. This was our displacement as a function of time with these d terms down here. Each of those is proportional to omega square. If we talk about now, compare the velocities, what we need to do is take the time derivative of this guy, gives us omega on the top, divided by omega to the 6, gives us roughly omega divided by omega over 5. We still have this a in here, which again is just basically a constant. It's omega naught squared divided by d, so the atomic resonance divided by lattice spacing. So what I want to do is now compare the two terms and see how they relate to each other. So if we divide now the atomic, so this velocity by the Lorentz one, by this guy, you can see that the E over m square kicks out, and you're basically left with this term right here. So a omega to the third divided by omega to the fifth times k. If you rewrite that, rewrite k, put your formula for a in here, reorder a little bit, you can actually see that it's pretty much given by lambda, the wavelengths, divided by 2 pi d, lattice spacing, and then you have these guys, omega naught square divided by omega square. Okay, let's take a look at two cases. So for X-rays, obviously our wavelength is approximately the length of a lattice spacing. So L is roughly d, which means this is pretty much 1. Say for omega naught, 1 eV is just the resonance, the absorption resonance for an atom. Omega X-rays is again 10,000, so 10 keV. You can use that, plug your omega 1 in here, you plug your 10 to the 4 square in here, and you can see that the Lorentz, the second order Lorentz velocity is about 10 to the 8 orders times the second order of the atomic one. Okay, so now we really have a nonlinearity that is strong at X-ray wavelengths and is not strong at optical wavelengths. Whereas if you plug in visible radiation, where your wavelength is on a micron roughly, so 10 to the 4 times an angstrom. Now for optical, you have omega naught about 1 eV equals omega, so this is 1. So this gives you, there you can see that the Lorentz one is about 10 to the minus 4 times the atomic one, and this is why in the optical, you usually use the atomic nonlinearities because it's much stronger, whereas for X-rays, our only bet are these Lorentz, these free electron gas nonlinearities. Okay, so we found a nonlinearity that is actually strong, strong enough for nonlinear X-ray effects. Let's just go briefly through these equations again. So we have these three terms. Assume our driving field as usual, and now we assume that both driving fields point at the same direction and are polarized parallel to each other, which means now if we take at the first term again, so there E1 is parallel to E2. You do your cross products, and you will find that this is just given by the product of the amplitudes times K2, the wave vector. Now this is a current, mind you. This is a current. The current is along the propagation of your radiation, which means that the emission will be perpendicular to that, which means your wave is propagating in, but your nonlinear response is basically perpendicular propagating out. So that's not too useful at this stage. Let's take a look at the second term. So E1 gradient dotted into gradient of E, gradient of E2. Gradient of E2 is just K2. We said that these polarizations are parallel, which means that E1 and K2 are perpendicular to each other, which means the term 2 equals 0. Now, third term, the gradient of the density. For uniform plasma, gradient of the density, of course, is 0, which means third term also 0. What we're left with is the emission that is perpendicular to the propagation direction due to this first Lorentz term. So basically, we're back to the Lorentz, the free electron case, but we don't have a viable nonlinearity in this case. Okay, now I have a question for you guys, but I couldn't make a good multiple choice out of it without giving away the answer. Does anybody see, so all of our three terms are basically useless. Does anybody see a method, a way how we could, now we have the strength of the nonlinearity would be fine, but all of these three terms so far are useless. Does anybody see a way how we could make this useful? Yes? You use all, well, okay, you can use different polarizations, yes, then, and probably different spatial fields, then you can, yes, you can direct it better. Another option, yes? Aha! Yes, use a crystal or something that does not have a uniform density, which means that your third term actually will not be 0, since the gradient of your density, if it's not uniform, you will actually get a gradient of your density. Very good. Your idea was good, but I go with that one. Okay, say we have a periodic charge density. So this term is still 0, but we usually use a crystal, and what we can do is just, so the crystal has a periodic charge density that we can Fourier expand in terms of the reciprocal lattice vectors, GM. This is what you do constantly in X-ray diffraction, which means that your density is basically just given by this Fourier expansion, where rho m are the Fourier amplitudes of the Fourier of the expansion. Again, as we said before, we have the first term. These guys are just E1. The first term is just E1 times E2 times K2. We have the electric field given right here. Look at the third term. Put in the electric field, take the gradient of this, and you will come to this equation right here, which is the second order current density at, again, oscillating at the frequency, the sum frequency, and for a periodic medium. So here we have our sum over rho m. This is the first term. This is the second term, that where the gradient basically gives you a g dot E2. And in the phase, we have this K1 plus K2 plus GM term. Okay? So if you fell asleep, now is a good time to wake up, because we use now this equation, discuss it briefly, and then see how we can apply this in experiments. So before we do that, we basically go back to what we did before. Take the inhomogeneous wave equation, plug in our polarization, or rather our current, noting that the current is just the time derivative of the polarization. Use our approximations, second order derivative, all of that stuff. This is our current. Do all of that, and you find that the phase matching, in this case, in a periodic medium for X-rays, is now given by this equation right here. So now we have the phase mismatch is basically K1 plus K2 plus the reciprocal lattice vector minus K of the sum of the two. And now, since we have X-rays, we use a periodic medium, we can use the reciprocal lattice vector to phase match the whole process. Okay? So we have a current density, and we have a phase matching. So we're back in business. All right, so this was the background. Now let me talk about the experiments that we can actually, we basically use these equations to discuss these experiments and to explain the experiments. Again, down conversion, parametric down conversion, optical some frequency generation, X-ray second harmonic generation, and then at the end, nonlinear X-ray Compton scattering. Okay, X-ray parametric down conversion. So what that means is you come in with one pump photon, and it spontaneously converts into two lower energy. One is called signal, and the other one idler photon. So you have one photon in, decays spontaneously into omega 1 and omega 2. A way to think about it is to think about the inverse process, or think about that as the inverse process of some frequency generation. Basically has the same matrix elements, but we can just basically, since what we talked about so far was some frequency generation, so we can use all of the formalism that we developed above to describe this effect. And in this case, if you now go through the phase matching condition, what you need is K1 plus K2 equals K pump, or K3 in this case, plus GM. This is the experiment that I talked before. Those guys used the X-ray tube, and then now we'll just briefly discuss it a little more. There has also been a theory paper before that, 1969, that was already describing these potential of doing this experiment. So what you do is you come in with your X-ray, you filter it spectrally, and then you come in with your pump. So this is your K pump. You use a beryllium crystal. And now this is your phase matching. So now you convert this photon, this incoming photon, to 2 red photons that are half the energy. The dotted line is where the Bragg reflection would be, but you're slightly off the Bragg reflection angle. And then you use some logic, because you only, if you get a click with the right photon energy in both detectors, it will count as a click, or as a count, and then you analyze all of that. Okay, so now this phase matching is basically what we said before, that K1 plus K2 are these two guys, equal to K pump plus our G, which in this case is the 1120 reciprocal lattice vector of the beryllium crystal. So you see you're not quite at the Bragg peak, but you're just slightly off of the Bragg peak with your signal. So here, for example, is so there's 2 detectors. What they did, they scanned the sample. So delta theta B goes from the Bragg condition. They slightly just scanned the signal, and you can see that they have a increasing signal where it's supposed to be. Basically, when this phase matching is true, then they get their signal, which again is roughly here 1.5 counts per 100 minutes. Okay, so we said before this is an X-ray tube. You need really big fields, high intensities to drive these nonlinearities. How do these guys get away with using an X-ray tube? Well, actually, and again, it was 400 hours of data collection, one count for one event per hour. If you go through the process, through the wave equation, calculate what the flux is of your signal, you see that you get it's proportional to the flux of your pump times the idler field square. Of course, the process that happens is there's no idler field. You just come in with a pump photon or with 1 photon, and it will decay into 2. So now we're basically at the end of our classical physics for briefly, because now this can only be explained, since it's a spontaneous decay, can only be explained by vacuum fluctuations that drive this spontaneous down conversion process. That means that you can think of it, you come in with your pump X-ray, it beats with 0-point fluctuations, and then eventually it will generate real signal and real idler photon. Again, the reason why this is so interesting is because the flux of the vacuum fluctuation scales as omega to the 4th, and is actually extremely huge for X-rays. So you get intensities of virtual intensities 10 to the 19 watts per square centimeter. You plug that in here, you see that even for an extremely weak source, you can see nonlinear effects. Okay, then while later there has been a down conversion experiment at a synchrotron, 1998. The first author name is that can't be coincidence. They now did the experiment with 19 keV photons. They had a much better source, better detectors, better signal to noise, higher count rate, and they actually measured now a very clean signal. It's still not huge count rates, but you can now actually measure a much better signal, a much more refined signal. Okay, so this process has been observed at synchrotrons, and now you can actually also use it for applications. So Kenji Tamesaku came up with a smart idea on how to use this down conversion, X-ray parametric down conversion, as basically a spatial resolution probe of the induced bond charge densities. All right, what that means is, again, we use the X-ray pump photon that decays into a signal and idler. You phase match it now, not that both decay into half of the photon energy, but that one of them is this where the photon energy is close to the pump photon energy, the signal, and the idler is just about 100 eV. So the experiment was done, I think, at about 8 keV. And now you basically what you do is you measure the signal photon scattering of the nonlinear density perturbation that is induced by the idler. So again, think of it as the inverse process of idler and signal coming in, generating the pump. That is shown here. So basically your idler is just 100 eV. Your pump then scatters off of that density. The idler induces a density variation. It induces a nonlinear chi, or at least a Fourier component of it, and then would generate a pump. And your down conversion is basically just the inverse process of that. You do that and measure your chi2 for multiple Fourier components. And if you know chi2, it's related to your linear chi, so your chi1. So you're basically can now, since you've measured that, can then reconstruct the linear density perturbation that you would have at if you drive your sample at 100 eV field. What they get out, and plus, since you do all of that in X-ray, you scatter X-rays off of this, you also get the advantage of having atomic spatial resolution of the experiment. When you do that, what the result that they come up, it's again diamond. They see for 100 eV, they see some contribution from the core. The core has a binding energy of 290, which oscillates in phase with the field. They can also determine with the phase of the oscillation. Since 100 eV is below 290, the bond charges are located in between the cores. They are roughly 12 eV, and since your 100 eV is above that, they oscillate out of phase with the field when they're more dense. So just using parametric down conversion, you can actually map for at least simple systems. You can map the induced charge polarization or the induced polarization in a material with atomic spatial resolution. Okay. X-ray optical sum frequency generation. This has been proposed already also in the 70s by these four guys. They were very productive. They came up with a theory, proposed the experiment, and here in this paper they actually mention if an X-ray laser is developed, then such processes could be used to shift X-ray laser outputs and so on and so forth. So personally I think we're lucky because we live in a time where X-ray lasers have just turned on. They do exist. We can do these experiments. Also the Higgs boson has been found and gravitational waves. So it's a very, very exciting times for physics. Okay, what is X-ray optical sum frequency generation? I think the name basically gives it away. You come in with an X-ray photon. You add an optical photon and you generate the sum of the two. The phase matching in this case is given by this equation right here. This is again our reciprocal lattice vector, k optical and plus k X-ray. A way to think about that is it's all due to this term back here that we said came from our first order induced density times the first order velocity. So a different way of thinking about that is that your optical frequency induces a charge density perturbation, and then your X-ray basically just inelastically diffracts off of this charge modulation, and then you get, instead of just your X-ray, you get an inelastic, either an addition or a subtraction of optical photon. This experiment has been performed as one of the first ones at LCLS 2012. Again, it's basically, think of it as inelastic X-ray scattering from the optically induced charge oscillations. Also, this experiment, besides demonstrating that you can mix X-rays and optics and optical photons, it's basically also a spatial probe of optically polarized charge on the atomic scale again. And you can measure principle if you know the induced charge, you can from then deduce what the microscopic electric fields are that are induced during the light-matter interaction. This information on the microscopic scale is not accessible through other methods, so you have to use this method, or this is the first method that actually, or the only so far, that can get you this information. And it basically can get you insights into the microscopic details of how optical light manipulates matter. This was the setup. Come in with LCLS, come in with an optical beam at 1.5 eV. So LCLS, 8 keV, about 40 femtoseconds. The optical laser was pretty long, 2 picosecond to ensure overlap. Fairly weak, of course. You mix it in diamond. Here again is our phase matching. Here's the diagram. And what you get is, of course, is a through beam, but then you also get a back diffraction. And then just off of the back refraction, there's an energy analyzer crystal and a detector. And here's what came out after the analyzer. So analyzer angle, and you can see this little blip here, which is your X-ray optical mixing signal. And here's just, if you compare that to, or if you convert that into relative energy off of the Bragg peak, you can see, or off the keV, that you can see it's 1.5 eV addition to the 8 keV. It sends very mixed signals. Okay, all right. You can also measure the rocking curve of the signal. It's a fairly narrow rocking curve. Dependence on the optical polarization. Of course, it only gives you a signal if the optical radiation, the field, points along the direction that you choose for your phase matching, and 0 if it's perpendicular to it. And you can do a temporal cross correlation of the optical and the X-ray. It's a fairly wide cross correlation because there's a group velocity mismatch. Well, it was a long optical pulse, but also there's a group velocity mismatch between the X-rays and the optical in the crystal. As I mentioned before, the optical radiation obviously mainly interacts with a valence charge, with a chemical bond charge, and your mixing signal then allows you to probe this charge. If you use, again, multiple Fourier components of it, it can be used to reconstruct the induced charge distribution. And you can, in principle, extend it to measure the full valence charge if you use UV or EUV X-ray mixing, but the cross-sections go down for that. And again, you measure, with this method, you can measure the linear susceptibility on a microscopic atomic length scale. So here's just a simulation that showed off diamond, that shows that here you can see diamond in the ground state. This is just charge distribution. Here you can see where the main induced charges are. So you can see here are the peaks, the high and low peaks. And if you overlay that, you can actually see that the induced charge peaks are basically also where the bond peaks are. So this is where the optical radiation mostly talks to. Okay, X-ray second harmonic generation. There has been a theory paper, 2003. So second harmonic generation, obviously you come in with 2 each omega photons. You generate a single 2 omega photon. Your phase matching in this case looks like this. K2 equals 2K1 plus your reciprocal lattice vector, shown right here. Now for X-rays, the index of refraction, well, this is actually not true. What that's supposed to mean is that the index of refraction of omega is fairly close to the index of refraction of 2 omega, which means that your phase matching is just slightly off of the Bragg condition in this case. What you do, you come in with your pump, so you use your fundamental photons. This is your phase matching, so you come in with the pump, you generate your second harmonic, and you just, since there's a spatial walk-off, you just generate it along this line, along the width of your fundamental beam. You generate it coherently, where it scales quadratic with the atomic density, and along your crystal, since you have walk-off at some point, it scales only incoherently or linearly with the diamond length or the diamond thickness. So this experiment has been performed at SLAC, at the SLAC FEL at a 7.3 keV, peak intensity 10 to the 16 watts per square centimeter, and target as often diamond crystal. Here's the setup. So the SLAC beam came in through a mono, was focused onto the diamond. There was a filter moving in and out to change the pulse energy pretty much. Then the second harmonic was generated. Here again is the phase matching, pointing out like this. There's filters in front and then a detector, that energy sensitive detector. And here's the result. If you scan the pulse energy and plot the second harmonic intensity, you can see that it's a quadratic dependence. It's an efficiency roughly that you would expect from the models that we just talked about. If you use these models, you get roughly the same, that it agrees with this efficiency. And you can, again, have a fairly narrow rocking curve, although it was a little wider than expected from theory. Okay, now let me come to the last part. So I told you that I'm going to talk about parametric scattering processes, which all of these were. The last one is a non-parametric process, and it's also quite different. So far we said that we basically can just approximate a solid as free electrons in the solid, calculate it. All of this fits perfectly well. The efficiencies are very close to what you would expect. The models fit fairly close to what you would expect. Now we wanted to test a little bit more about what the quantum response of the whole system is. So we still talk about X-rays, X-ray scattering, where you have your photon energy is quite a significant part of the electron rest mass, and where you would expect at least some quantum effects. We did this experiment, got actually a cover which was very nice. We got a news in view straight out of Compton, which is also kind of cool. Okay, so what is nonlinear Compton scattering? Well, now we go from a plasma, we go more to a particle view, to a quantum view. So you have basically now two photons scattering simultaneously at an electron. And when you do that, then they emit a single photon at roughly twice the photon energy, but a little less, since the electron gets a recoil and takes some energy and momentum away. The experiment was done at 9 keV, and the shift of this from the 18 keV was about 600 eV to 1 keV. Experiment was done at LCLS, focused the hell out of the beam. You get, as we said before, huge peak intensities. If you do that, 10 to the 20 watts per square centimeter, 10 to the 13 volts per meter field, well above the electric field, atomic electric field, within 5 orders of the QED critical field. So this is serious fields that you have there. And now I have to introduce, unfortunately, one more parameter, which is, I could tie it back to, this is basically nothing else. We're looking again at our Lorentz figure 8 motion. I'll show that. But there's another quantity that plasma physicists like, which is the so-called normalized vector potential, where you have the energy that an electron gains within of the electric field within a wavelength divided by the rest mass of the electron. If this quantity is roughly 1, you talk that the electron gains or moves with relativistic velocities. Now we said we have huge fields, but at 9 keV, since lambda is so small, your A naught is still only about 10 to the minus 3, so still fairly small, where with optical fields this would be a factor of 10 probably, or something like that. This is interesting because it allows to investigate a regime of high fields, yet small ponderomotive potential, where the ponderomotive potential scales as this A naught square, A naught very small ponderomotive potential, yet high fields. Okay, we found out that if you subject an electron to such a field, it will do a figure-8 motion. If you calculate now the spatial emission of this figure-8 motion, of course, to first order, you will get a dipole emission. It looks like this. To second order, you get this quadrupole emission that looks like this. It is peaked in the back direction, about 135 degrees. This is due to the interference of the electron, excuse me, of the electron moving back and forth in a quadrupole emission pattern. Now, I said that the photon energy you can calculate, so you transfer some momentum to the electron, and the amount of momentum that you transfer to the electron depends on the observation angle. It's mainly given due to the recoil. There's also something that is called relativistic mass increase, but it scales as A0 square, which is an extremely small number in this case. But in this experiment, we looked at 90 degrees to 130 degrees, and you see a shift of about 600 eV to a 1 keV from your 18 keV photon that you would expect. Just a few, I don't want to go through this since I'm running out of time. You come in basically with the full LCLS beam, 10 to the 12 photons. What you end up is per shot, you maybe get like 1 or less than 1 nonlinear photons per detector. So it's a good way to destroy lots of X-ray photons, but also to get some good physics out of it, of course. Here's the setup. So we use LCLS beam, focus it down. There's silicon attenuators where you can change the pulse energy. You focus it on we use the beryllium target, 4 detectors at different observation angles, so you can see different scattering angles. Most of the beam is transmitted, and then we have a second target chamber out of focus where the field are much smaller. And here, you basically, this is to just see whatever background we have, any linear scattering, since the FEL also will have some second harmonic that comes through, to have a good feeling about the background. So the data that I will show you is basically histograms of these detectors. So here, this detector is at 90 degrees scattering, then you go to 135 degrees. The top row is for the front chamber, where it's a high intensity, and the bottom row is always out of focus, where we have the linear, where we have the background. These histograms basically show you the detectors have a bit of an energy resolution, so they will show you if you have no photon, which is this main peak, a 9 keV photon, or an 18 keV photon. Okay, then what we did, change the FEL transmission, start out low, turn up the machine, turn it up to 70% and to 100%. And what you see here again, so this is now photon energy. You can see this huge second harmonic signal coming out of noise in the front chamber, whereas in the back chamber you pretty much see nothing. There's also much different scale here, as you can see. So you can clearly see this nonlinear signal being actually generated. Although it was so small, it actually was a quite surprisingly clear signal. If you integrate all of the second harmonic, the photons around 18 keV versus FEL transmission, you can see again that this is a quadratic dependence, as you would expect from a second order effect. The blue one is the reference chamber, which is basically straight, or you can zoom in, you can see that it's just maybe slightly increasing linearly. And as we had this News and Views article, straight out of Compton, and this joke is copyrighted by David. What they actually wanted to say, straight on a log-log plot, out of Compton. Okay, we also scanned the position of the sample. You can see a clear increase as we scan the position. Here's the integrated signal again. It peaks when we're in focus, and it then decreases quite a bit when we're out of focus. And again, the back chamber pretty much didn't see any change. It's just random fluctuation. So we basically know that we have a nonlinear signal right there. One more thing that we did is that we were able to look at coarsely look at the spectrum. And again, here's the shift off of the 18 keV, about 600 eV to a 1 keV shift, depending on the observation angle. The way we looked at the photon energy, we didn't have a spectrometer back then, but what we had is zirconium filters in front of the detector that cut down the fundamental, but it also has an edge at 18 keV, which means that we scanned the FEL photon energy going from 8.8, say, to 9.3. So this is a plot of the transmission, by the way, about 10 to the minus 2. You have 10 to the minus 7. So that signal basically just gets absorbed by the foil. We still see the part of the Compton signal, but then we increase the photon energy even more, and all of the signal should be absorbed by the foil. Okay, when we do that, this is the result, and let me just walk you briefly through this result. Let me first look at the back chamber. So this is where we probably see linear scattering of the second FEL harmonic at 90 degrees to 135 degrees. This is the Compton shift that we expect. This is the signal, 8.8 keV photons. We increase the photon energy, it starts decreasing a bit. We increase it more, 9.2, 9.4. 9.4 means here's the smallest shift. So this is where it basically is completely absorbed by the zirconium foil. If you calculate that, you roughly get to a shift of 500 eV, which you would expect. You increase it more. Now you can see here, this guy starts to crab out. It's about 900 eV shift. Again, fits with what you would expect. Increase it to 9.6 fundamental, and finally 9.75. You can see that now the black line, there's basically no transmission on the back chamber, on this low intensity chamber, and the shifts that we see are about what you would expect. Now if you look at the front chamber, do the same game, 8.8, 9, 9.2, 9.4. The back one starts to decrease quite a bit. No signs of it in the front. 9.5, 9.6, 9.7. The increase here is probably because we had less statistics, but there's no single sign that we see any decrease of the signal at all. This was completely unexpected, and as I told you before, we would have expected something, a model that we were talking about, that explains all these other experiments so wonderfully, but we did not. This was absolutely not what we did expect. 2 minutes. Okay, 9.7 keV means if that makes it through the zirconium, you basically what you talk about, you have about an additional shift of about 800 eV. That was again absolutely unexpected. We were able to go back to LCLS in February, look at the plasma temperature. If that was an effect, if that was the reason, it was just a really hot plasma that we shifted and broadened it. We did that with Siegfried Glenzer's group. Since I'm running out of time, I'll give you the short answer. It is not the case. From our measurements, we see that the plasma is fairly cold, just about 8 eV, whereas in order for us to explain the shift that we see, we would need a 300 eV hot plasma. So the plasma is out of question as an explanation. We also did some few more investigations of different frequencies. Let me just very briefly tell you why this is so surprising. So for a free electron, what we would expect is you can come in with 2 photons. We look at 90 degrees. This is a scattered photon. This is your change in momentum. You transfer the energy to the electron. That's all fine with free electrons. What we observe is that we have a much smaller transfer in momentum. The outgoing photon is a lower energy, which means that the electron would have to take up a lot more momentum and energy, which is not possible for a free electron. So something has to take up the momentum, and currently what we think it is that the whole atom is actually interacting with the X-rays and not only free electrons. And now if you go to quantum mechanics, You can calculate that, and there's a model, or we came up with a model that could, in principle, explain it, but we still need to verify that if that is really true. If it's true, then we would have observed a scattering mechanism that has not been observed before, and is only possible to be observed with X-rays. Plus, huge intensities, we can drill 100 nanometer holes in a beryllium foil with X-rays. It's also what we found on the way. Okay, before Mariano kicks me off, I have to be a shameless self-advertiser. I have an open postdoc position in my group. If any of this, what you heard today from me, sounded interesting to you, send me an email, just contact me, or do raise your sheet yellow or something, and then we can talk. Okay, this is my references, and thank you very much for your attention.
Questions? Non-linear questions? Yeah. Yeah. So I was wondering if you have anything like, perspective comment about this particular experiment. If you use this the way to extract some information about either the valence structure of the material or some, something that you cannot do with current linear methods, for example. I don't know.
So we have to verify if our model is correct. If this is really this model is really true. If this really is a new scattering mechanism, there would be a potential that we can even phase match this, which would increase the efficiency quite a bit, and we could use it as a diagnostic. And there is a chance that, for example, you get X-ray diffraction. You not only would get, since this will interact with the whole atom, but there's this what's called this A.P terms, which is also has a chemical specificity, I guess. You could not only get spatial information, but potentially also information about the chemical structure of your atom that you have.
Okay. And the phase matching also helps because you don't necessarily need to destroy your sample.
Yeah, you don't. Yeah, you don't need square miles of sample.
Right. Which will also be difficult to do at LCLS too, right?
Yes.
Are there any questions over here? So I think we are done with talks for now. We have a coffee break. And then after that, we have the LCLS talks. There's going to be 2 talks. There's going to be essentially 2 talks, the hard X-ray and soft X-ray talks about the LCLS. So that's going to be about roughly an hour. And then after that, I hope you guys are somewhat set up in teams. And if you don't have a team to work with, talk to me, or just either talk to me, or we'll find a way to set you up with some team for the poster. Okay. And any questions about this, you can come talk to me. I'll be here. So, thanks.
For more, please visit us at stanford.edu.